Let's continue. So one of the things that is very important when we go forward is that we're talking about roots of polynomials, right? And when you talk about roots of polynomials, you are in general can be dealing with complex numbers, because not if you want to really factor them all the way, you have to really think about the complex numbers. So we'll do a quick review of complex numbers. Again, this is not by any means a complete review or complete course in complex numbers or things of that sort. So this is like a very short complex number reviews, but I want to make sure that everyone's on the same page. So what is a complex number? Let's start with that. What is your, how would you define a complex number? Yes? A plus bj. Okay. What does that mean? Okay. So, and imaginary numbers are numbers like 11, 30, 12. Yes, exactly. Good one. I used exactly the same numbers, actually.
Yes, you did.
I have good memory. Yes. 11, and 30, 12. Yes, Calvin and Hobbes. Okay. Yeah, sorry. Confess. Guilty as charged. All right. So now, what in terms of imaginary numbers, what do we mean by that? What are imaginary numbers? Okay. Okay. So you say square root of -1, but what is that? Yes. I mean, everything you're saying is correct, right? I'm poking because I want to get to the fundamental meaning of these things. It's not that anything you're saying is incorrect. So what is it? What are these things? Now, there are different ways to think about it. One way is what you said, is like say, okay, if there were a solution to this equation, that solution in normal mathematics they call it I, right? Which is basically you can show as square root of -1, but also you can and from this point on, as electrical engineers, we show it with J because we don't want it to get confused with the current I. So from this point on, J is I, right? But anyway, so that's one way to think about it. But as a complex number, you said it's A plus JB, which is okay, fine. It really isn't one way to think about a pair of numbers. It's an ordered pair. So complex numbers. And if you think about it, you can think about them as an ordered pair. What's an ordered pair? Let's say you have x and y. You can say x and y. And when you say ordered pair, it means that in general it's not equal to y and x. The order matters, as opposed to a set where the order doesn't matter. So if you have an x and a y, what does that define on the plane, on a 2D plane? It defines a point, or you could think about it as defining a vector from the origin to that point. So it's a vector. It's a pair of numbers. It's an ordered pair, right? X and y. And you can show it like you said. You can say, okay, z, this new number, is x plus jy. So there are two ways to show this. One is, for example, in two-dimensional plane, you can show it in the Cartesian coordinates, which is x and y, which is this representation, or you can show it in polar coordinates, which is what? R and theta, right? So you can have these two representations of the same thing, of this number. By the way, complex numbers, as you can see, are generalization of numbers, right? I mean, so you start with integers. If you start with integers, then you go, first you start with the natural numbers, then you add the 0, which is a big deal. Then you do the negative numbers, you get the z. Then you make the rational numbers, right? The ratios of any arbitrary z, right? And then you find that there's a lot more irrational numbers than rational numbers. Rational numbers are between any two rational numbers, there are a very, very large infinite number of irrational numbers. So the density of irrational numbers is much higher than rational numbers. If you think mathematically, you may have seen this. So if you look between 0 and 1, and if you look at density of, there's a more accurate way of defining it, they say measure. It comes from measure theory. But anyway, it means that there are a lot more, infinitely more irrational numbers than there are rational numbers between these 2 points. So rational numbers are very sparse. Irrational numbers are very dense in there. So most of them are irrational numbers. So you go to the irrational numbers. Basically, then you add the irrational numbers to rational numbers, you get the real numbers, the R. And then you go and generalize one level higher, which is basically kind of a simple generalization. So, well, okay, 2 of these, a pair of these. But the pair of them have some interesting properties, as we'll see. Now, but does it stop there? What is the next level up? Quaternions, right? So it's a 4 numbers, order of 4 numbers in an order. And there are some relationships that are even kind of similar to this, but generalized. But when you do quaternions, what happens is that you lose the commutative property. So quaternions in multiplications are not commutative. Complex numbers are. In other words, z1, z2 is equal to z2, z1. But when you go to quaternions, that's not true. But quaternions are actually quite useful, even in computer graphics, things of that sort, in these orders of magnitude things. So actually, a lot of times they are used. So it's a pair. It's 4 numbers: x, y, z, t. How? So it's you can think about it as a point in four dimensions, a vector in 4 dimensions. And what happens is that there are certain rules. So there, instead of 1j or 1i, you have 3. So there's a 1, there's a I, there's a J, and there's a K. And their multiplication is interesting, kind of like it's rotational. So you have a multiplication table for these things that 1 times 1 is 1, 1 times I is I, but I times I is J, etc., etc. So they rotate. They also relate to the totally antisymmetric element epsilon I, J, K that you may have seen in physics or somewhere. But anyway, so we're not talking about quaternions here. Let's stick with the complex numbers. So it's a pair of numbers, and it can define it this way. So you can define it in this form. And if I define it in this form, and if I wanted to express x and y in terms of r and theta, what would they be? What is x in terms of r and theta? X is r cosine of theta, and then y is r sine of theta. Right? So therefore, I can write z as r cosine of theta plus j r sine of theta, which I can write as r cosine of theta plus j sine of theta. Okay? Now, you can think of this. There's another way to represent this or that. You can say it's r theta. Sometimes you put the angle there, sometimes not. So this is a symbol for saying it's the vector with magnitude r and angle theta. That's a symbol, and we'll use this symbol from time to time. Now, for a complex number, there's also another number. For every complex number, there's another one which we call the complex conjugate, which shows with the z asterisk. And what it is basically x minus jy. Essentially, the real part remains the same. The complex number changes sign. The imaginary part changes sign. Now, all of these are basic definitions. Something that's quite useful and interesting and important is there's another way of showing this, and there's a way to calculate this. So let me ask you this question. What is e to the x, the expansion, the series definition of e to the x? You remember that? It's 1 plus x divided by 1 factorial plus x squared over 2 factorial. Yeah, so on and so forth. 3 factorial, x to the 4 factorial. I can keep going. Right, so that e to the x. It's really x to the 0 divided by 0 factorial, the first term, really, if you think about it. But now, what is the expansion? Do we remember the expansion definition of cosine of theta? 1 minus theta squared over 2 factorial plus theta to the 4th, 4 factorial, etc., etc. And sine is theta minus theta cubed over 3 factorial plus theta 5 to the 5 factorial, and so on and so forth. So now let's try to see what this is, if you can plug it in. Or let's try to do something actually a little bit different first. So let's do the e, see what is e to the j theta going to be based on this expansion. So what is it going to be? 1 is 1. So what is now the first term? Is j theta, right? The second term is j squared theta squared. What's j squared? J, we defined it, right, to be square root of -1. So it's -1, negative theta squared over 2 factorial. So what's j cubed? Minus j theta cubed to the 3 factorial. Next one is j to the 4th. What is j to the 4th? 1. So it's theta 4 over 4 factorial plus j theta 5 to the 5 factorial, and so on and so forth, right? So now look at this and see if you can identify bits and pieces of that in here. So if I take these terms, what do I get? What are those terms that I have a red line underneath? Right. So those are the cos of theta. And then how about the ones with the blue underneath them? J sine of theta. So e to the j theta is that, but that's what we had here. So now you can write this as r e to the j theta. So this is equal to that. You can see it from here. This is called the Euler's relationship. And it tells you some interesting things. For example, it tells you what e to the j pi is. What is e to the j pi? Well, cosine of theta and cosine of pi and sine of, what's cosine of pi? -1. And what is sine of pi? 0. So this is -1, so that basically tells you this. And when they found this, actually, well, for this I'm going to make an exception. Just for that one. Because, you know, when they found this, when they wrote this, they thought this is the root of all math. This is the most important thing, equation in math. First, they said, because it relates e, pi, I, and 1, and 0 to each other, right? These are the most important numbers in mathematics. 0, 1, pi, e, and j, or I. It's another relationship, but anyway. Okay. So that was interesting. So, side note. But this is the useful part. This is the useful thing called the de Moivre relationship. So now, if you write it this way, it allows you to multiply the complex numbers. So for example, in a more easier fashion. So for example, if you have z1 and z2 multiplied, you can write them as r1 e to the j theta 1 and r2 e to the j theta 2. And you can write as r1 r2 e to the j theta 1 plus theta 2, because these are in an exponential, the argument of an exponential, they add. So you can write it this way. This is also useful for calculating certain geometric, you can get a lot of basic definitions of trigonometric functions. But the most useful one, for example, is what is cosine and sine in terms of e to the j theta, right? So if I take this and look at its conjugate, complex conjugate. So the complex conjugate is going to be e to the negative j theta. Basically, I'm looking at this function evaluated for negative theta. So cosine is a symmetric function, so it wouldn't matter, right? So it would give still cosine of negative theta is cosine of theta. But cosine of sine of negative theta is negative sine of theta. So I have this relationship. Now if I take these two together and add them, what do I get? I get cosine of theta is e to the j theta plus e to the negative j theta divided by 2, because these two add and these two cancel. So I get 2 cosine of theta is e to the j theta plus e to the negative j theta And if I divide it by 2, I get this relationship, which is a very, very useful thing, and we'll use it extensively. These we'll use extensively, so if you have forgotten about them, good time to refresh your memory. Now, how about sine of theta? How do I calculate sine of theta from these two? Subtract, right? Subtract this from that, so I get e to the j theta minus e to the negative j theta divided by 2j. So these are useful expressions that we'll use when we are dealing with sine and cosine. They are useful because they allow us to deal with sine and cosine as exponentials, right? And you remember when we were seeing this exponential, say, well, this is a special case of complex frequencies and all those things. So now you can see that you can actually write sines and cosines also as exponential. So you can see that all of these can be written as exponentials because of this relationship. Now, also these are useful for calculating things. For example, if you want to calculate, if you don't remember, does anyone remember what cosine of 3 theta is in terms of cosine of theta? Do you guys remember it? No. I almost don't. So yeah, I mean, I have to kind of like say, okay, what was it? It's this. So, but what I do, and from now on you can do the same thing. Use this. You can calculate cosine of n theta if you're interested, and sine of n theta. How do we use that? So this is a useful application of this thing. So calculate e to the j theta to the power of n. Let's say, or if you're interested in n. I'm going to do it for 3 for now, but in general for 3. So if I calculate that, we know from the exponentials this is equal to the e to the j 3 theta, right? But also I know what this is. So each one of them can be written differently. This guy is written as cosine. So let me just reorder this. Write it as e to the j 3 theta equals e to the j theta to the 3. So this left-hand side is cosine of 3 theta plus j sine of 3 theta. You agree, right? It's this. I just replaced theta with 3 theta. Agreed? Now the right-hand side is I'm going to use this inside the parentheses first. Say cosine of theta plus j sine of theta to the power of 3. Right? And so I plug this into this guy and got it to the power of 3. So I need to just, now hopefully I know how to calculate this. Right? Binomial. So this is cosine 3, cosine cubed of theta plus what? Plus 3j cosine square of theta sine of theta plus 3 or minus. Now this is going to be this squared, so it gives me minus that squared, which is basically cosine sine squared of theta, and then minus this cubed, which gives me minus j sine cube of theta. So can I find cosine of 3 theta from this? Yeah. The real parts of the left-hand side and right-hand side have to be equal. Right? So this part has to be equal to all the real terms, this term and that term. So that tells me cosine of 3 theta is cosine cube of theta minus 3 cosine of theta sine squared of theta. The part that I always struggle with is that which one was square, which one was not, etc. If I want to remember it. And then also the red parts, the imaginary parts, have to be equal. Right? Which gives you sine squared too. So you get sine squared, sine of 3 theta as well. Sine of 3 theta is going to be what? So I just drop all the j's. So I get 3 cosine squared theta sine theta minus sine cube theta. Right? So you can actually derive it. You can do it for n. You can do it for 2, 3, whatever your favorite number is. So this essentially captures all of those trigonometric identities that you had to memorize or something like that. All of them is just collapsed into one thing, really, which is easy to calculate. So if I ask you to do, I mean, I wouldn't, but if I asked you to do that, like what is cosine of 4 theta, you know how to do that, right? Okay, so this is the basics, very basic complex numbers. So that's fine, but we'll use it for something relevant for us. Any questions on complex numbers before I move on? So we are going to use it particularly to look at a general second order response of a system. So in other words, we are looking at so in a situation where you have a polynomial of the form p squared plus ap plus b. This is useful for differential equations that are in the form of, y double prime plus a y prime plus by equals x. Right? So if you're trying to solve those things, you're dealing with terms like that. Now, in our terminology and in electrical engineering, and essentially in a lot of engineering, when you're dealing with second order systems, there's a nicer, better, more meaningful form to write these things. The more meaningful form is like this: p squared plus omega n over q p plus omega n squared. Now, there are 2 degrees of freedom here. You have omega n and q, and there are 2 degrees of freedom, a and b, in terms of equations. So you can always find an omega n and q that satisfy this. But these are useful things because they relate to the natural frequency of the system and its quality factor, or how much loss there is in it. So this is called the quality factor. This is an important parameter, and this is called the natural frequency. So now we know that if you have a complex numbers, then you can factor any second order polynomial into product of 2 first order polynomials, right? The only thing is that sometimes the roots will be complex. Right? If you think about the quadratic equation, the solution to the quadratic equation, if the term under the square root becomes negative, then you get complex numbers. If the term under the square root becomes positive, or you get real numbers. And if it's 0, you get a pair of duplicate roots. So in general, then I can write this in the following form: 1 over p plus a, 1 over p plus b, as 2 operators, product of 2 operators. So the inverse operator will be something like this. If I write the differential equation this way, then y of t would be the 2 inverse operators operating in succession. We did this last time, so I'm just doing it very quickly, right? This part of it we did last time. So now we know what this is. I am interested, for example, let's say we are interested in knowing the impulse response of a general second order system. That's a useful thing, right? Because if you know the impulse response of a system, what can you do with that? What can you calculate with it? If I give you the impulse response of a system, an LTI system, do you know everything you need to know about it? Right. So if I gave you an arbitrary input, how do you calculate that, the output of that arbitrary input if you know the impulse response? Convolution, right? You convolve the 2 of them. So let's find out the impulse response of an arbitrary second order system. So the first thing we are going to do, what is that? So the impulse response, h of t, is going to be 1 over p plus b, 1 over p plus a of the delta of t. That's the input x of t, right? The impulse response. So this is the impulse response of a second order system. Okay, so do you agree that I can apply them in succession? So it would be 1 over p plus b of this. What is this? We have defined this before, right? We calculated that. So it's e to the negative at, 1 over p, e to the at, delta of t. I'm just using the thing that we derived last time. So what is this? Can I simplify this a little bit more? E to the AT delta of t. Do I care about the value of e to the AT at any time other than t equals 0? What is this value at t equals 0? 1. So this basically becomes just 1. So this becomes 1 over p plus b e to the negative AT 1 over p of delta of t. Okay, so let's apply the second operator first. Now, so what is the second operator? This one. It's going to be e to the negative bt 1 over p e to the bt times what is left of that, which is e to the negative at. And what is 1 over p of delta of t? U of t, right? This should become, you should start knowing these things cold. The integral of the delta is the step. So it's going to be u of t. So this is basically, it says that in general, the impulse response of a second order system is e to the negative b minus at u of t. 1 over p of that times e to the negative bt. So this is the impulse response in general. Now we will evaluate it for 3 different scenarios. Case 1. When they're both real. So essentially both real, A and B are real. So you have real roots, like 1 and 2, negative 1. And they're not equal. A not equal to B. So there are 2 different roots, independent roots. So in the 3 cases, I basically apply that condition to these and see what the answer would be. Find it exactly. So this is what we are going to be doing now. So in this case, h of t is going to be what? If they are real, then can we do more with this integral? So can we calculate this thing? I'm just rewriting it here. I just copied that here. So what do we do with that? Something happened. Can we calculate this? How? Anyone wants to take a stab at it? How can we simplify this? Yes. Catherine, right? Oh, Kathleen. Yeah, sorry. Yeah, go ahead. Say again? Yeah. Pull out the u of t and change the limit of integration, right? So negative bt u of t integral from 0 to t e to the negative b minus a of t dt. So now what is this integral? Right. What is the indefinite integral first? I mean, you're correct. I'm just trying to break it down into 2 steps. You're right. So I take that out, 1 minus b minus a, e to the negative bt, u of t, and then I'm evaluating it for e to the negative. So I'm evaluating at t and 0, right? So it becomes e to the negative b minus a, t minus 1. You agree? That's good? So we need to just simplify that. We are done, but we need to simplify. If we multiply out the e to the minus bt, what do we get? Yes, exactly. You get e to the negative 8. You get e to the negative. So I'm going to switch to, oh, that's fine. E to the negative bt. Oh, I'm sorry. E to the negative at minus e to the negative bt u of t. So that's the impulse response for the system. Does it make sense? So what do you see? In the impulse response, when the poles are real, or what the natural frequencies or the roots are real, I said poles, but that's not incorrect. But I jumped ahead a little bit. But, OK, we'll get to poles and zeros. soon. But anyway, when the roots are real, what do I get? I get two exponentials, two real exponentials. So what does it look like, the impulse response in time domain? So I have these two. I have an e to the at, right? So these are exponentials decaying, right? So these are decaying exponentials times u of t. So let's say we said one of them, let's say assume one of the time constants is greater than the other ones, right? So it's like e to the at, or negative at, rather. And there's now e to the negative bt, which let's say has a faster time constant, right? So it's a difference of these two. How will that look like? At 0, what is it at t equals 0? 0, right? So the impulse response of this thing goes up and exponentially goes down. It may not become that large for the things that I plotted, but just it's not to scale, right? Because first they're equal, one of them grows faster, starts gaining on the other one, and then you just lose the other one and then come back. So the impulse response of this thing looks like this. It's just like it goes up, it comes back down. That's assuming one thing, though. That's assuming that A and B are both greater than 0. What happens if one of them is smaller than 0, of the A and B? What happens with these exponentials? Go ahead. It just keeps growing, right? It blows up. So if they are positive, A or B, negative, I'm saying, one of them is negative, then it will grow exponentially, because then it becomes a positive exponential with a positive exponent with time. Yes?
Did you say that's unstable?
Yes, that's an unstable system. We'll talk about stability later. Also, we'll talk about stability. But yes, that's an unstable system. This is a stable system. An impulse response that grows without bounds is unstable. Is almost the definition of an unstable system. But that's good. All right? So that's one case. So how many more cases do we have to do? There's this kind of a special case.
Question.
Yes?
So in that case, the B and the A are, it's like if we have like a circuit with like capacitor and inductor, the B and the A are going to be the respective taus for the...
Not necessarily. They may be two different things. I mean, if they had a capacitor and an inductor, it depends on the values. Usually when you have a capacitor and inductor, if the resistors are not too large, you don't get this. You get case 3.
Okay.
This is probably a case where you have, for example, 2 capacitors.
Okay.
Something, for example, something like this can produce something of that nature. These are 2 real cases. If you have a capacitor and inductor, usually what you get a system with complex roots. Again, not always, but I mean, it depends. I mean, of course, you can have a tiny capacitor and a large resistor that would just dominate it. So case 2 is when basically A and B are equal. Sure. That depends on the values, right? So basically, if you want to know where it peaks, you really need to optimize this. You need to differentiate it and set it to 0, and then you will see where it is. It's not a fixed. I mean, you can calculate what that is. And even the value of the peak depends on the relative sizes, right? Because if A and B are close, then the peak is going to be very small. The farther the 2 time constants are, or the 2 natural frequencies are. That's it. Good question. Any other questions? No? All right. So if A is B, again, let's go back to that general expression, this one, and now apply it in this case. So if again, in that case, h of t would be e to the negative bt, 1 over p, e to the b minus a t, u of t. Now, in this case, it becomes simple, because what happens to this guy, this term? Goes to 1, right? So because this is 0, so this becomes 1 if they are equal. So what you're left with is something that's easy to calculate, 1 over p of u of t. What is 1 over p of u of t? it's t u of t, right? So it gives you e to the negative a or b, which are the same thing, a t or bt, t u of t. Or you can even actually put the t up front. That's more common. So write it this way. So this is the impulse response. Again, the impulse response, if you look at it, it's something that is 0 at time t equals 0 because of the t, and then goes back up and comes back down. So it qualitatively looks similar to that. Yes?
So it doesn't matter if they can be real or imaginary in case 2?
No, they're real. Sorry. They're both real. Still real. So and the reason we are thinking about, so why are we thinking about these three cases? Think about the roots of a quadratic equation, right? Either you get two reals, or I get a duplicate pole, right? Duplicate root, basically you get this two of the same root, when the square root becomes 0, right? The plus and minus. So what are the roots of the classic one quadratic equation? If you write it the standard way, you get negative b plus minus square root of b squared minus 4ac divided by 2b, right? 2a, sorry. I'm forgetting. It would be useless because then it would be b divided by b. So this is the x, right? Now, what happens if this is real? If this is greater than 0, this becomes, you get two real poles, two real roots. Now, if this is 0, you get two identical. This is case 2. If this becomes negative, then you get a pair of complex conjugate roots, right? Why are they complex conjugate? Because the real part is the same, and their imaginary parts have opposite polarities. So you get something like x plus jy and x minus jy. So the roots of this second quadratic equation are not any arbitrary complex numbers. Either they are two reals, or they are the same root repeated twice, the same root twice, or a pair of complex conjugate numbers. It can't be just two arbitrary complex numbers. Yes?
Going from e to the negative bt, 1 over p u sub t.
Uh-huh.
Is that supposed to be a bt?
I basically throw a in there because a is equal to b.
Okay.
You could write it this way too. They are the same, right? Because in this case, they are the same thing. Okay? Any other questions? All right. Let's do case 3. So case 3 is where we are going to use our complex numbers. Oops. All right, so now case 3 is when a and b are complex, but we know they're going to come in complex conjugate pairs. So a and b are complex, but a conjugate is going to be b, which means that you can also write them in the following form. You can write them as a equals sigma plus j omega, and b as sigma minus j omega. So this is the real part, and this is the imaginary part. I just call it sigma and omega. So now if I do this, if I plug them into that, take that equation that I had again, the general solution, h of t, was e to the negative bt, 1 over p, e to the b minus a t, u of t, right? So now let's plug them in. Let's plug them in this form, because this guarantees that they're complex conjugates, right? In these forms. So now we write it as e to the negative sigma t times e to the positive j omega t, right? For that term, 1 over p. Now, what is b minus a? The real parts cancel, so you get e to the negative 2 j omega t, right? And u of t. So that's what I need to calculate. So come down here, say h of t. Now I have to calculate this integral. Again, so I have e to the negative sigma t, e to the plus j omega t, And then I'm calculating this integral. I pull out the u of t and change the limit of integration. So I get e to the negative 2j omega t dt. Now, this integral is easy to calculate, right? It's an exponential. The indefinite integral is 1 over this coefficient times the exponential. So e to the sigma t, e to the plus j omega t, u of t, times what? This evaluated for t, well, there's a 1 over negative 2j omega here, and then I get e to the negative 2j omega t minus 1. Right? This comes out of integration, this denominator. And this is basically the two evaluated at the two limits. So what do I get? I multiply this thing out. So I get e to the negative sigma t over omega. And I can leave the rest of the stuff here. The j omega t, negative j omega t. Now I get e to the negative, this times that, gets rid of the 2. So I get negative j omega t. And the other one gives me e to the positive j omega t. Right? So if I take this minus, if I look at this whole thing, what is this? Yes, sine. Right? Can everyone see that this is the sine? So what you're left with is, actually, I have to bring this omega down here too. I have to put the omega down there because if I want to make it the sine. So it becomes e to the negative sigma t, and I drop the u of t at some point. Just put it back. Sine of omega t u of t. Wait a second, no. No, I shouldn't put the omega back here. Omega is still here. Because I just need the 2j. So there would be an omega here. So what I get is 1 over omega, right? Sorry. So I get e to the negative sigma t over omega sine of omega t u of t. That's the impulse response. What does this mean? Look at this. This looks very different, right? So, but although I went to the complex numbers, what came out is completely real. Which should be, because I started with real things and just like expanded in the complex domain. It has to, if you get complex things out here, it means that you've made a mistake. Because the real system being hit with the real impulse, it should generate some real output. So it is a real output. What does it look like? What does this thing look like? It's a sine wave, except for the fact that there's an exponential decay. So what it looks like is this, where this is that exponential. This is e to the negative sigma t. So it's a decaying sinusoidal, assuming that sigma is greater than 0. But that's not necessarily the case, right? What if sigma is smaller than 0? What happens? Yeah, it grows, right? So if sigma is greater than 0, then what happens is that you start this sine and then it keeps growing. So you can, and what if sigma is 0? You get just a sine, right? I mean half sine because it starts from t equals 0. So you can see that it subsumes the sine waves, the exponentially decaying and exponentially growing sine waves. So you can see that the second order shows all of these interesting behavior. It shows the exponentials, it shows the exponentially growing sines and the decaying sine and sine wave. And you will see later on that these are actually what the complex frequencies mean. So So remember these three behaviors, and when next time we'll talk about, we will apply them and see how we can use them. All right. Any questions?